Yes, so could you explain the diagram again? All your
This
explanation.
is capital R is the region in which B field is varying. Magnetic field is varying. Okay, dear?
Yes.
If B field varies, then EMF will get induced.
Yes.
And that EMF is related to field, which is what we call induced electric field, it being non-conservative and non-electrostatic in nature. We studied about it. There was a reference to it the other day, correct?
Yes, sir.
Now this E that I have marked over here, if I am to find value of E, I'll write E dot dl and will integrate it over the loop. Find what we mark in accordance with Faraday law of electromagnetic induction, d phi by dt, correct?
Yes, sir.
Okay, so E dot dl is equal to d phi by dt. Or to be precise, you can superimpose. There can be a precursor minus sign minus of d phi by dt, no issue, direction being known to us. Now, E will be constant is what I'm professing next. And this I can profess only in this case. I presume you must have the reminiscences of what we did on that day in the class, let vis-a-vis E transpire. I told you that owing to symmetry, E will be equal everywhere on the circle, provided we have a change of field in a cylindrical orientation. If not, if it is not cylindrical, if it is any other form, then we cannot profess the same. We can only for cylindrical exhibition of B field, correct?
Yes, sir.
So E being constant, E is out, dl will get me 2 pi r, which I do right over here. Flux is nothing but into, what do we say? Pi r square, because we are referring to this area. B by dt. What we end up getting, E into 2 pi r is equal to pi r square dB by dt. Okay?
Yes, sir.
Okay, from here, gone. We get, sorry, gone. We get from here E is equal to R by 2 dV by dt. So this is how E varies. E doesn't vary with H. And if you look at the equation, I wrote this equation the other day. R
Yes,
by
sir.
2 dV by dt, correct?
Yes, sir.
So the E that we got, H by 2 dV by dt, is a constant, and that constant when multiplied with L will get me potential difference across the ends of the rod taken, right?
Yes, sir.
But that is not E. E you can see in my second derivation where I have used R by 2 dB by dt cos theta. Cos theta was replaced by H by R, right?
Yes, sir.
Yeah. So please be careful. This is E to me. What about E when I have taken capital R lesser or smaller than small r? How will you write it down there? Will this assumption hold water or not? Will
So
this
which
assumption
assumption?
of E on a circular configuration constant hold merit or not?
Yes, sir, I didn't hear you. What assumption are you talking about?
The assumption which we are on over here with, and you want conformity with it, which being E on this circle everywhere will be same on magnitude. Only then you approved of this E being taken out of integration, correct?
Yes, sir.
So induced electric field, we are of the opinion, we are into touting, it'll be same on this circle. And this is true only for the case when we are having B changing in cylindrical zone, correct?
Yes, sir.
If B changes in any other zone, let us say B was changing in a cubical zone, right?
Yes, sir.
I would not have taken E to be constant on this circle. Nobody would have approved of it, correct?
So, are you saying it'll still Okay, I have a couple of questions here. What does this circle exactly represent?
This circle represents the flow of current. There is a conductor placed channelized. If I place a conductor over here, then
Yes.
current will start circulating in this manner. And if current is circulating in this manner, or for that matter, let me make it bereft of current for now. There's no current, let's say. I ask you, how will E field get configured in this zone? What will you say? How will E get configured in this zone? Which zone? The zone in which B field is changing. First and the foremost, you must be in conformity with, there will be an EMF induced, right?
Yes.
So EMF got induced. I want to show induced electric field to which EMF is attributed to. Find here?
Yes.
EMF will not be attributed to magnetic field. It will be attributed only to electric field, correct?
Mm-hmm.
So EMF is getting induced, but this EMF is attributed to a field, and that field being non-conservative, non-electrostatic in nature, we have a precursor for it, it being induced. Induced electric field will be in what configuration present here? That was the question. What will be the configuration? So the configuration, and I am finding refuge in symmetry because B is in cylindrical zone. So E can be, owing to symmetry, said to be configured a circle, family of circles, correct? Different position will represent different value, right?
Yes, sir.
But over this circle, over a radius, over one radius circle, E will be same on magnitude. With this idea being coined, I took E out of integration, correct?
Yes, sir.
And then equated with what did Faraday profess? He did profess E dot dr or EMF is equal to d phi by dt, right? They are same.
Yes.
Either you say E dot dr or you say E equal to d phi by dt, correct?
Mm-hmm.
Because E has marked it as EMF. EMF is equal to minus of d phi by dt. EMF is equal to minus of d phi by dt. And the other way of writing EMF, if we take a leaf out of our electrostatic portion, is E dot dr integration, correct?
Sir?
The other way of writing EMF is E dot dr integration, right? Yeah.
Yes, yes, yes.
And as it is on closed loop, so the circle is representing the closed loop, and E being constant, we have ideated E being constant, E taken out, integration falls on DL. DL when integrated will get you 2 pi r, right? Yeah.
Yes, sir. So that's yeah, okay, yes, I got it.
Which is what got us this with the minus, I have taken minus now. So which is what got us this, right? E is equal to minus of r by 2 dv by dt. Minus plus is as per your understanding. Okay,
Yes.
dear?
Yes.
Okay, so E is equal to minus of r by 2 dv by dt. I asked you, can we do the same? Can we state with equal ferocity, were B field found changing in a cubical zone?
So my first question would be: would the current flows as you've drawn happen to be circles when the B field is changing in a cylindrical containment?
Yes.
Will there still be circles when it's varying in this
Yes,
cuboid?
it will be circles because current will be flowing courtesy E field. E field will push the charges, right?
Yes, sir.
And E will keep on changing. Okay, dear, over here it'll be in this direction. So I won't say it'll be exactly circular in shape because it'll also gain some acceleration in this direction. But in a Jilch, if you are to say, yes, it'll be a circle.
It'll be a circle, but the magnitude of E field won't be same everywhere on the circumference.
Magnitude of the circumference per se will not be same, dear. If the radius changes, only then the current is to change. If radius remains, why will current change? Current
Must be-
depends on E, and E
Yes,
is
sir.
constant for a particular value of R.
So I recall you saying that E is not constant for a particular
Because
value of
of
R
the
when you're
direction,
talking.
yeah, magnitude, not direction. I'm taking only magnitude into consideration. E is equal to minus of R by 2. R for a given R, it will be the same, right?
No, maybe I'm mistaken. What was exactly the distinction you drew in the E field between the cylindrical and cuboidal containers?
Cylindrical is this to us. Cross section is this to us.
Yes, sir.
This is capital R. I took
Yes.
small r, and I
Yes.
have, in this case, for this configuration indicated, E being same everywhere on this circle. Okay.
Yes, sir.
This is the ideation that I am in.
Yes, sir.
And
So if you
this
trans
ideation, the proclivity to this ideation is B being varied in a cylindrical zone which has got circular cross-sectional area. Correct, dear?
yes, sir. So what exactly changes when you put that in a cuboidal box?
Steps from there. Steps from there. As shown now, right? Right?
So could you repeat? I didn't hear you.
If I take the configuration which I'm showing now, this is the cross-sectional area of the configuration. Okay?
Yes, sir.
Here I cannot, with same ferocity, I'll say, I cannot with same ferocity say that E will exist in the circular region. With same magnitude, I will not be able to. Why? Because this is not symmetric. What E you will get over here will not be the same what you get over here. Getting it here?
Yes, sir. So
E will
yes,
not be same on magnitude.
yes, sir.
Here E was said to be same. As the case being symmetric, take any point, you can rotate, it will be back to this point, or you can take the shape of any other point. It is symmetric, taken any point on the circle, right?
Yes, sir.
Towards the configuration of B variance. Correct?
Yes.
Which is not the case here, right? Getting it?
Yes, sir. So that circle, that loop is still a circle of constant radius. Yes. So you're saying for a fixed radius, magnitude of E will not be constant.
They'll be different not only on direction but also on magnitude. Okay. E1 will not be equal to E2. We cannot state symmetry here. Here it was reasoned out owing to symmetrical case. The symmetrical case exhibition is a cessation now. Symmetrical case exhibition is a cessation now. Can we say that?
Yes, sir.
Okay. Therefore, it holds, this one holds only for which variation? Cylindrical variation of B field. Agreed, yeah?
Yes, sir.
Okay. Question number 2, which I was at. Okay, B field is varying in this region. This is capital R. I want to calculate somewhere over here, B field. Can I make the same assumption? The assumption of on circle, this is capital R, B field is varying in this capital R zone. I want to find B field at this position, at the position smaller from the center, where small r is greater than capital R. Can I make good the same assumption here? Can I make good the same assumption of symmetric case here? Can I buttress the same?
Yes, I would say yes.
Yes, we can. What are we then to write? E into 2 pi small r, correct?
Yes, sir. Is equal
Is
to
equal
pi r
to
square
what
dv by dt.
Now, help me write. is equal to
pi r squared dv by dt, capital R.
Which
Capital.
are? Yeah, pi capital R square dv by dt. Okay, if so required, a minus. What do we get from here? E is equal to R square by 2, right? E is equal to capital R square by 2R into dv by dt, correct?
Yes, sir.
If so, d minus. So these are the values of induced electric field for a cylindrical disturbance of magnetic field. Cases are less than capital R or greater than capital R in tandem. Are less than capital R or greater than capital R in tandem. Got an idea?
Yes, sir.
Sure.
Yes.
This is important and is important vis-a-vis advanced IIT. Means they may not touch, but in advance they are certainly to us. It's a specific case. Means we'll go with ambivalent cases. Okay, dear?
Yes, sir.
Okay, fine. I asked a question over here, which is a follow-up of previous class. In the previous segment, we learned omega L over here pivoted, B omega L square by 2 will be the EMF across the ends, right?
Yes, sir.
I have a question over here, which will be getting us some insight on what to do for the case incoming. This will help you in solving the case incoming, by the way. There is a rod for me, length L. This end is V1 and this end is moving with V2. It is in B field. What would you say over here will be the EMF induced across the ends of the rod? How will you work it out? In this case, V1, V2 known to you, L known to you, you can calculate omega, you're aware of it, right?
Yes.
So omega, if you wish, get, mathematically, you will be getting it as shown, right? Yeah.
So maybe you can split the motion into two components, translational and rotational. We know the formula for translation anyways, and then you add on top of that the rotational motion.
My question is to be brought to perspective first. So let me steer it to what I want to know of you.
Yes.
So far as omega is concerned, omega is gotten by V1 minus V2 by L, right?
Yes.
So are we in a position, are we in our liberties to use the previous equation with this omega replacement?
But it's not pure rotational motion, is it?
No, it is not.
So I don't think we can use that.
What shall we do in that case?
I just suggested maybe we can apply this formula and use the integral V cross B dot dl formula to get the EMF due to its translation motion. Is that
okay?
Right?
Okay, yeah, that'll work. Certainly that'll work. And that is what we have to, but then we will have to relate which point will be the point about which you can assume the rod to be rotating, which is what we call in technical terms
Instantaneous
Yes.
center of rotation.
of rotation. How are you to locate it? Where will it be spotted? Can you tell me?
So it's got something to do with the ratios of V2 and V1.
So what can we say? Let be somewhere over here at a distance x, right? Yeah.
This is, I think you can say that V1R is equal, yes, sir. Yeah, sure. V1R is equal to V2R.
L into omega, right?
Yes.
And V2 accordingly is equal to x into omega. These equations are then going to help us in finding relation and accordingly, as you did suggest, integrating. By integration, you'll get to know a formula which can be used in a short now. Okay, but
Yes.
you get that formula. Once you have gotten, you'll be able to use for different cases, and you will be able to use in one stroke. The different cases which may come to you now is being brought. The one which I was talking about. This is a circle. It's rolling without slipping. EMF across B field present everywhere. It is rolling without slipping. If I ask you what will be B field inflicting here in terms of induced EMF, what will you say? What will it inflict?
So could you repeat the question again?
This is a circle. Circle is rolling without slipping in presence of magnetic field directed into the green board, let's say. Find EMF induced in this circle per se. What will be EMF induced in this circle?
So maybe you can use the same instantaneous axis of rotation thing. We can take the bottom to be the instantaneous axis of rotation, right? The point at which it makes contact with the ground.
Okay, good.
And from
We can simply connect this, right? That'll do. If you've gotten this instantaneous axis of rotation, then you need not go for this integration. You can directly connect and you get it, right?
Yes, yeah, you can do that too.
Okay, now I do ask you for the case when it is rolling with slipping.
So then you'll have to do some gymnastics to get the instantaneous axis of rotation. Right?
Nothing else. Yeah, exactly the same. Exactly the same. We'll be using this only, right?
Yes, sir. You just need to locate the instantaneous axis of rotation.
Yes, and when you will locate one, we will be mindful of integration will not take place from here, it will take place from here.
So what?
Integration should not take place from here. If you locate it comes out to be over here, let us say ICR, then integration, when you're integrating, you'll integrate for the length of the rod, be it this case or this case, right? Any student after finding ICR, they integrate from x is equal to 0 to x is equal to over here also they will do the same. If I get you V is equal to 2R omega and you get V is equal to 2R omega, you get okay, it is a distance R. Then what they will do, the mistake, the part that this, I would say, skip off their mind, generally it does happen. From here, from 0 to 2R they do. You are not to integrate from 0 to 2R, you have to integrate from the presence. And presence is at R to commence. So from R to 2R, correct?
Yes, sir.
Okay. So this was about one of an example set, I would say, which I want to deal with you today. And the other questions from that set being as follows. Write down. This one I wish you will get me the answer to. So I get you 2 minutes to it. There is a circular loop. There is a circular loop of resistance R, capital R, of resistance capital R, when rotated by 180 degree about one of its diameters, when rotated by 180 degree about one of its diameters, find charge that will flow through its segment. Find charge that will flow through its segment. Any segment you can take, this segment, this segment, this segment, any part. What charge will flow through that segment?
Yeah, okay. So basically, you want integral I dot dt for the entire time.
Correct.
Okay.
We take into the board. What charge will flow through any of the segment you deem? What is the attendance you are running here? The attendance which you are running, is it good at school, at your college or not?
So I would say it's moderate. I mean, it's not stellar, but it's good enough. I've been keeping a close eye on the 70% mark.
You are still on with this quaint idea, snoozing and groveling for attendance, right?
Yes, it's mostly just for attendance.
Okay.
I mean, the sad thing is they don't even let you do anything else there. So yeah, it's not a great. These teachers just like have these extremely huge egos, so I mean they won't let you do anything else.
They are basically control freak and they are control lawn on the aspect. So wherever they feel free to exercise, they do. Beyond with snoozing and groveling, as they call, can't do a thing about it. Yeah, but then within the self-respect zone, don't start cocoing. What would it be? It will not take for Vasudev this long. Come on, Vasudev.
Yes. So you know that the EMF is going to be R by 2 dV by dt.
All right.
From the okay. So ultimately, yeah. Okay. If that's the EMF, basically what you want is E dot.
Right.
Wait 1 second. E dot dt over the entire time. So well, R is constant, so you'll get R by 2 integral dB.
Let me over here correct you. B is not changing with time.
Yes, no, so like you can talk about it in a relative sense, right? The okay, B is not changing.
Yeah, B is not changing with time.
Yes, but
you
like
just now did add R by 2 dV by dt, correct?
yes, it's fine. Okay, I got my mistake. I got my mistake.
Shall we start with the formula, Vasudev?
Yes, sure.
What is E? Tell me. Scaffold, I won't be getting you the answer. I'll be just throwing few hints and you'll get it on your own, of course. What is the formula? E is equal to EMF is equal
yes,
to?
So like I think it would be better if we start from the beginning here. So E times 2 pi r is equal to pi r squared sine theta.
Correct. Yeah, we can start with that, but that is electric field. I'm not finding electric field over here. I'm finding EMF.
Yes, sir.
This is, of course, this is equal to, if you want me to write, I'll do the same for you. E dot dr, right?
Yes.
Fine, done, right?
Yes.
So instead of getting capital E, I'm getting the italics E. Why? Because it'll be easier for me. I wish find Q. Q is equal to I into dt, as you know, right?
Yes, sir.
And I is nothing but E by R.
Yes.
Dt, right?
Yes.
And E dt is nothing but d phi.
Yes.
So delta phi by R. Now this is the formula for you. You know what to do.
Okay, so
Delta
basically
phi.
delta phi by r.
Yeah.
Just give me 1 second.
Yeah.
About 1 if it's ends. Find charge that flows through. All right. So it goes to 0 to 0 pi r squared. Will it be 2 pi r squared?
What is it?
Delta. No, wait. Delta phi. Wait, 1 second. Phi is
B into the B into area.
Yeah. Yes. So the change in area is 0 to pi r squared and then back to 0. So 2 pi r squared.
It was this way. Initially, it was this way. So if I am to ask you what is phi 1, phi initial. Phi initial, B is inward, area is outward, so minus of B into pi small r square, right? B dot ds.
Yes, sir.
And phi final. Now, phi final, area rotated.
Yes.
Area rotated and area is going towards the B field now. So B into pi r square will be final, correct?
Yes, so it's 2 pi r b, the final answer. 2 pi r b.
So the two r are different.
Oh, are they?
Resistance. Yeah, this r is resistance.
Okay, fine. I actually cancelled them.
The r is resistance.
Yes, I got it. 2
Okay.
pi r squared b by resistance. Yes.
Got it?
Yes, got it.
Okay. The other question, write down.
So also, could you take the question we left halfway last time your connection just dropped? I think it was the
Right.
semi-infinite wire going into a plane.
Yes. You remind, right? So there we were dealing with a situation wherein it was this way, and then if I can draw it for you because the orientation of board got changed this way, and the wire is going somewhere like this.
Yes.
Right, infinitely spread wire. Infinitely spread network rather. Okay.
Yes.
And then we got to see that if I draw B field line here above it, then I was getting in this form, right? This way.
Yes, sir.
Which I did drop on it. I'll be dropping it on it. I'll be dropping again on it. This is the one that I'm getting. I'm dropping on it. I'm showing it to you for the horizontal case. Okay, dear, this is the case. It is going this way, right?
Yes, sir.
I drop, it goes this way.
Okay.
One go this way, the other go up. Okay, from this, one go this way, the other go up, right?
So the other?
The other component, this is B field. B field is this way, right? This way.
Okay, talking about components. Okay, fine. All right.
Okay, one go this way on the plane,
Yes.
right? This,
Yes.
correct. And the other go up, right?
Yes.
The other go up. Look at it. I'm drawing over here. This is the one. This is the one that I will be paying heat to. The other one will get anyway cancelled. We'll come to that. So this one. Now this one, which is on the plane, which is on the disk, infinitely spread disk, will break in two components. One goes this way.
Yes.
And the other this way, right?
Yes.
Go this way. And the other this way. Getting it?
Yes, sir.
So we got altogether three parts it being broken in. One is vertically upwards. The other is away from me. And the other is this way, correct? Left of me.
Yes, sir.
Now come to the other part which I was referring to, the circle for the other part of the wire. This was for this part of the wire, now for this part of the wire, right? No, sorry. This was for this part of the wire, entire wire.
Yes.
Entire wire, half going this way current, half going this way current. We got in three part broken.
Yes.
Now you take the counter of it, this one.
The perpendicular version.
Yeah.
Okay.
This one, this wire. One wire you took this one.
Yes.
For this wire you got how many direction? Direction into the board, direction to the left and up. Three directions, correct?
Yes.
Now you are taking this one, let's say. Again curling of finger, getting it? What I'm trying to suggest. Yes. I'm bringing it to you. Wait, look at this. This will make it get it clearer. This was the case?
Yes.
Okay. Now wire we have taken it over here. Here it was taken this way, right? This is the B field.
Yes.
Because of which wire? This wire. This wire. This wire, correct? This
Yes.
was the wire, correct? Because of that you got B field in this direction, right?
Yes, sir.
It dropped here. took one component this way, the
Yes.
other component this way, and
Yes.
the third as we have dropped upward, right?
Yes.
Okay. Now I ask you for the same position which is over here. Which wire we will be taking now? This wire, from here to here. Down. From here to here. Okay. How will be the B field this way? Agreed? Just curl
Which
the finger, you
wire?
get that.
So which wire did you take?
First case was wire, this one, right?
So I can't exactly see what you're doing. The field of view of the camera is too small.
Okay. Look, this is the wire. And this is the other wire, okay? Two wires shown.
Oh, you've actually drawn. Oh, yeah. Yes. Okay.
These
Alright.
are the wire where on the disk, correct?
Yes, sir.
Due to this one first, where I have to find B field? Here.
Yes.
Not on x-axis, but above. Here, if I can show, I have to find it over here, above it, right? Here, correct?
Yes, sir. I get the point. Yeah.
Okay, so I bring it over here now. Let's say I have to find here.
Yes, sir.
Okay. I get B field this way. Check it out. Curling of the finger, B field over here will be this way. Yeah.
Yeah. Got it. Yeah.
Think about it. Huh? Right?
Yes, sir.
And that B field we placed on this, now I'm placing over here. It breaks into one component and the other component. This component I'm breaking in this component and this component. Okay.
Yes, sir.
So up, away from me, and to my left, I got three, correct?
Yes, sir.
Okay. Now tell me about this one. This one, if you'll curl finger, you'll get it in this direction or not? This one, this way, that downward or not? Check it out. Check, curl the finger and then check it out. For which one we have got in which direction, you are to define. For this one, first for this one, I'm coming.
Yes.
First for this one, it was this way.
Yes, sir.
It was going this way, right?
Yes.
It was going this way.
Yes, sir.
Now for this one. Where
Yes.
again on this, right?
Yes, sir.
This way, it'll go this way. It'll go this way.
Yes. Okay. So the chalk is pointing downwards, right?
Yes.
Okay. Yes.
Go this way here. Just think about it. Curl your finger, it'll go down here. And when you're taking this one, then you're curling your finger, you're going this way there.
Yes.
One will go down, the other will go up. Think about it. Check it out here. Don't be in a hurry. Because this is to be understood. This will not be made understandable. They will write one statement and it's done. I'm repeating. Current going this way. Okay?
Yes, sir.
This is the center.
Yes.
I want to find direction of B field where? Here.
Yes. So wait just a second. Let's just call those quadrants something. The leftmost one is quadrant 1. The bottommost one is quadrant 2. So right now your point is in quadrant 3. I am
finding field not on the quadrant here. I'll tell you where I'm
finding. I know it's above in space, but just assume if you project it onto the plane, where would it lie?
This one, this point on the plane.
Oh yes.
Above x-axis.
Okay, so that's your x-axis, fine. All right.
Yes. So I curl my finger now, okay?
Yes, sir.
I make circles, correct?
Yes.
I get on this a circle which is of this orientation, like this, right?
Yes, sir.
This is the direction of B field on it, right?
Yes, it's going from bottom to top. It's pointed upwards.
This way, it go this way, right?
Yes, sir.
Which I'm breaking into components, I said, right?
Yes, sir.
One is vertical.
Mm-hmm.
Okay, dropped on it. One is away from me, this way.
Yes.
And the other is to my right, correct? Check it out.
Yes. Yes, I got it.
I repeat, this way, one up, dropped here, away from me, to my right, correct?
Yes, sir.
Okay. Now due to this one, curling of the finger. Okay.
Yes,
how it goes this way? It goes this way.
So 1 second. Wouldn't it be the other way? Yes.
All are out. Current being out here. Current being this way, this way, this way. Due to this one, this one, this one. We did for this one first.
Yes, sir.
Now for this one. I am to find here. The point remains.
Yes, sir.
I'll curl my finger. Points here. I curl
Yes.
my finger. I'll get downward, right? How will I get upward? Here I
Yes,
was
sir.
getting upward because it was
Yes, sir.
coming this way. It will be downward.
Yes, sir. So I'm just saying it should be downwards to the right. Why are you saying to the left? I mean, it's to the left. It's to the right, right? Downwards, pointing to the right.
This way, this way, this way. This one was up this way.
Yes, sir.
This one was up this way.
Yes.
This one will be down this way. Same, this direction only. It was up, right? This one
Yes.
was up.
Yes.
Up was broken into two, dear. See, this is up. Up doesn't mean vertically up. Up
No,
means
I'm not saying what.
finished.
Yes, I know what I'm saying.
Okay, fine. Now what I do, I take up and drop it. Drop it on the
Yes.
plane. So I get away from me and this one will be to the right, correct?
Yes, sir.
If it is dropped on the plane this way, then I break in this component away from me and then the right.
Yes, I got that.
Now I curl my finger for this one. I get this way, right? Check.
Just one
this one.
second. I'll just curl my fingers and have a look at it.
This one, and again on that x-axis, but not exactly on x-axis, same point over here. I curl my finger. What kind of circle I am to get? Think about it. How will it be?
Yes, sir. No. What I'm saying is, I agree with the direction of the first field you got, but for the direction of the magnetic field to the second wire, it will curl that way. But since the point is above the plane, won't the direction be pointing towards the board? Roughly
You mean to say
towards
this
the.
way?
Yeah, I mean to say that way.
The point we have taken over here, right?
Yes, sir.
Fine. We have taken point over here. It'll
Yes,
be this
sir.
way.
Yes, that's what was confusing me. Yes, okay. Fine.
Correct. It'll be this way.
Yes.
For this point, the point that we have taken will be this way. Okay?
Yes.
Okay. Now what you got? One down. One component of it will be vertically downwards.
Yes, sir.
What about the other component? It was this way. You have dropped it over here, correct? On the plane.
Yes, sir.
This goes into, and this goes to my left.
Yes, sir. So the ones that go to your left and right from the two different things cancel out.
They will cancel. Up, down also cancel.
So the only one that's remaining is going towards the board.
Exactly. So that part remains, and this part also is to produce going into the board, correct?
Yes, sir.
This part. So here what will you get is addition.
Yes.
And here what you will get is subtraction. So this portion, this plus the other part will collectively get you same what you'll be getting for an infinitely long wire. Why? Because we saw that ultimately what we are going to get for this portion is addition, correct?
Yes.
And addition into the board, which is in consonance with what this is to produce, what semi-infinite is to produce, correct?
Yes, sir, but how can we ascertain on the magnitude?
How can we ascertain on the magnitude? We are getting for all the portion in terms of the angle. We will be getting for different angle, different value, right? Yeah, I'll fix a point of radius r, and then I'll have to integrate it over the angle.
Yeah, okay, so you'll basically have to turn this plus a configuration around 90 degrees.
Yes.
Okay.
This will get you an addition, but this will get you below it, as you can see for yourself now. You can curl your finger and see for yourself.
Yes.
For the portion below. For the portion below, you'll get outwards. Outwards, the net field. And outward and this inward will cancel each other.
So below the plane, there's no field.
Below the disk. This will be producing inward anyway, right? Below the disk also will be producing inward, correct?
Yes.
But this effect will be outward. Outward. Okay?
So what's the net field there? Is it 0?
That is 0. This will be 0. This will be 0.
Okay.
Below will be 0. Above will be same or akin to what we get for infinitely long wire.
Yes, sir.
Got it here?
Yes, sir. Got it.
Okay. Now I take a quick one or two with electrostatic concept. One is this. This is a charge capacitor. C, Q is the charge on it, C is the capacitance on it. And what we do, this is a conductor taken, B field. Okay. Now there is no resistor anywhere. What I do is, there is no resistor anywhere. Sorry, I said resistance. There's no resistor anywhere. What I do is, I connect it. Okay. So horizontal arrangement, there's capacitor which is fully charged to Q.
Hmm.
There is B field present in the entire of the zone. This is a conductor. There is no resistor present anywhere, no resistance, no resistor. When you switch it on, okay, mass of conductor is known to you. Capacitor not required for now. We'll introduce it later. Mass of conductor known.
So that's like a sliding rail. Is it?
Yeah.
Okay.
Sliding rail. When you cut, what will be the consequence of connection? Well, let me ask you a question. What velocity will the connector start moving? What velocity will the connector start moving or will gain?
So we can. Actually, my question is, if to determine its velocity, we will have to determine its current, right? The current flowing through the wire.
True.
Yeah, but then there's no resistance here, which means the current will be infinity.
True.
So infinite velocity.
So you get impulse owing to that infinite current, yeah?
I mean, it has to. It has to be some finite. You can't just exactly say there's no
It cannot be
resistance.
infinite. Infinite will be this term. What you're referring to is, if I'm to find f dt and integrate, then I'll get it equal to mv, right?
Yes.
And f dt, as you said, is ilb dt, right?
Hmm.
So I dt is nothing but q lb being constant, right?
Yes.
We get v from here, right?
Yes.
Getting it?
Yeah. Okay. All right. So essentially, what we're doing is, okay, fine. I get the rough essence.
These are the
You're just
ones.
transferring all the energy from the capacitor, and you're not exactly bothered how in what time frame it takes place.
Be careful, Vasudev. We have to prepare these questions. Okay, let me bring it one more to you. Let me bring it to you. This one. This is moving with velocity v naught initially, right?
Yes.
Let me bring it to you. Another one. Shall I bring it to you?
Yes.
Okay, moving with velocity, m is given to you. Let me take resistance this time. Mass m, radius r, mass m, sorry, not radius, resistance r. B field present through and through. What will be the effect? R is in these conductors. It is not in the rails. The rails are free of resistance. Find here?
Yes.
Not to be seen in the rails, only the conductors.
Yes. So what did you ask for?
What will be the effect? What will be the eventual velocity? Or velocity as function of time?
Since the rail is moving away, that will cause a positive d phi by dt or negative, depending on how you look at it. Either way, it will induce a current.
Correct.
And
What will be of that current? Will it pull it along?
Yeah, the end due to well, 1 second. Let me just think about it. It goes down. It increases that way. Okay, the current will be clockwise, so anti-clockwise, the way we're looking at it, right?
I'll compartmentalize my question in two asks. Ask
Yes.
number one, because ask number one you can get directly without much indulgence. Ask number one, what will be the final velocity? Ask number two, substantiate your answer by indicating velocity as function of time. Ask one is simple. It's on your intellect, your astute, your spunk. Tell me what will it be? What is the final velocity? What will be the final velocity of the rods? V final, V1 final, V2 final.
Okay, just 1 second. So the rod which is already moving, I think it'll come to a stop.
Okay.
No, because look, eventually there has to be a release of energy in the circuit. It can't perpetually perform something like SHM. So eventually it should come to a halt, right? Because there is energy being dissipated through the resistors.
Okay.
So
So want energy dissipation to cease, right?
yes.
Okay. I'm not in odds with your idea. There should be a cessation.
Yes. So if energy is being dissipated after some eventual amount of time, it'll stop whatever it's doing.
Energy, see, there is a difference between what you are suggesting and what I am trying to profess.
Yes.
You are of the opinion that energy should drop to a zero.
Yes.
Station will happen, according to you, only when energy drops to a zero, correct?
Yes.
There can be other aspect of what you are reading. The other aspect being cessation takes place by making the constant a drop. That drop is reduced to zero. That drop is reduced to zero, or that drop is reduced to a constant.
So what?
In either case, the either is, of course, on the same line of thought. What that mean? No dissipation anymore.
Yes, I didn't get what you just said. The drop will become constant. I didn't understand that
You
part.
are of the opinion that will drop to zero, right?
Yes, sir. Yes, I understand.
Energy will drop to zero, only then there will be a cessation taking place.
Yes.
Right?
Yes.
I'm of the opinion cessation in drop will certainly take place, but energy is not dropping to zero.
Okay. All right. So how could that be done? The only way I can see energy being stored here is the kinetic energy of the rods, and if that is there, the magnetic force will still be acting, right?
No, second one I'm not in conformity with. First one I am. The only energy which I can see over here at this point in time is kinetic energy. And then what is to be done, what will happen? Of course, current will start flowing, right? And if current flows, energy will be lost, right?
Yes.
If I want that energy to be retained, to be not equating to zero, kinetic form of energy to be maintained,
Yes.
I'll have to make current zero. I'll have to make current zero. I'll have to make current zero.
Yes, no, but let's say at the end, energy is a non-zero quantity. That means some part of this setup should be moving. Either one of those rods should be moving with a finite velocity.
Of course.
Yes, and then if it is moving, it's moving in a magnetic field. Won't that generate an EMF?
I impress upon my point. I impress upon my point, which being, let us arrest flow of current. Let us arrest flow of current. I am taking a reverse logic. Why? Because you started with the premise energy. So I'll go
Yes,
by energy,
okay.
no doubt about it.
I think I know what you're getting. He'll have both of them move at the same velocity, so there'll be no d phi by dt.
Exactly. Now you're talking, Vasudev. That's it.
Yes. So yeah, that could
They will
happen.
move with same velocity. They
Yes.
will move with same velocity.
Yes.
There'll be no change in flux, no current then.
Yes.
That'll be the eventual case. And when you know that, you know you can conserve momentum.
Yes.
Right? There is no external force. Conserving momentum will get you V1 is equal to V2 is equal to V0 by 2.
Yes.
Got there?
Yes, got it.
Okay. Now tell me V1 as function of time, how will I get? Or V2 as function of time, how will I get? I want V1 or V2 as function of time. Fine. Take it that way. Assume it to be, what we assume it to be? V2, let's say, correct?
Yes, just 1 second. I have a little doubt from the last assertion you made. You said you can conserve momentum here.
Yeah, we can conserve momentum.
Yeah, but the magnetic field is acting. I mean, is acting. I mean, applying a force on these things, right?
For the system, I'm conserving for a system. They are applying force on each other. It's internal force, external.
Oh, it's that way. Like the force on one is equal to the force on the other.
Let's check it. Why can't we check it? Let's check. I current flows, correct?
Yes.
Is moving this way.
Okay, the same current is flowing through both of them, of course. No, never mind.
V1, let us say at any point in time, right, Vasudev?
Yes.
So what potential? V1BL? V1BL, potential difference, correct?
Yes.
This is moving with velocity V2, let us say, what potential across it? V2BL?
Yes.
Check it out. Intermediate situation, V1, V2, fine.
Mm-hmm.
And you can justify movement because if you take only this to be moving, current will flow in this direction, then force on it will be in this direction, you can justify. F will be I into L cross B, right? So L cross B will be this way, right?
Yes.
I, L this way, B this way, L cross B to the right, correct?
Yes, sir.
So on this force will be to the right, which will be ILB. On this force will be to the left, which will be again ILB, right?
Yes, sir.
Okay. We write equation for this one. What will it be? Force to the right, ILB. F is equal to what do we have? Tell me. Mass into acceleration, mdv by dt?
Yes.
Okay. Force is how much? For us to maintain over here, ILB is equal to what I write? M into dv by dt, right here?
Yes, sir.
Now what about I? What about I? Which one is greater? This one is greater. So V1LB minus V2LB divided by 2R. That is I, correct?
So V1LB and wait, just give me 1 second.
Emotional. Positive, negative. Positive, negative.
Yes, okay, yeah, now it makes sense. You subtracted them. Okay.
R is resistance over here, correct?
Yes.
One equation. The other equation, you know, conservation of momentum, right? Yeah.
Yes.
mv naught is equal to mv1 plus m. This is the second equation. The two equation will get you v as a function of time. Can you?
Yes.
You can remove v2 from here because we are focusing on v1, let's say.
Yes.
Place I there and get me v2 as function of time. A tad bit of integration required, nothing much. Not difficult. M is same. So v0 is equal to v1 plus v2. v2 will be removed by v0 minus v1, correct?
Yes, sir.
Can I come up to v value?
V1 minus V2 LB squared by 2R dt. Yeah, F is equal to M.
V2 can be replaced by or replaced by?
Yes, sir. V2 is equal to V0 minus V1.
Correct.
So 2V1 minus V0. So basically you get dV by 2V1 minus V0 is equal to LB whole squared by
Write that
2R.
down. dV by what did we say? 2V0?
dV by 2V1 minus V0.
2V1 minus V0 is equal to?
LB whole squared by 2R, or L squared B squared by 2R.
Square by 2R into dt, right?
Yes.
V1. This also will be V1 then? dV1?
Yeah, okay. Yeah, it'll be V1.
What do we get from here? dV1 by V1 minus V0 by 2. Right? Yeah, that taken out. LB squared 2R dt. So we get ln of
V1 minus V0 by 2.
LB square by R into dt, right?
So dt, didn't you integrate?
Somewhere, I think we have missed M somewhere.
So M,
yeah.
F is equal to M. Oh yeah, I think I did miss M there. F is equal to M dV by dt. ILB is equal to M dV by dt. Okay, you'll get dV is equal to, okay, that it's 2Rm. You will have it 2Rm there. 2Rm. Yes.
So you got from here, right? Equation from where to where? V1 is to vary. We'll say from V1 was which one taken? This one. So V0 to V final, right?
V final. We know V final, right? We know V final is V1 by 2.
No, V final we have to find.
Oh, okay, no,
We don't know V final.
sorry, I got it. We are trying to find velocity as a function of time, of course.
Yes.
Alright.
This will be a time constant. What you're getting L square B square by 2mr will be a time constant for you. This will be a time constant. We'll be getting V1 as, this is equation akin to, I'll say, Dobganger to what we got in
Capacitance?
Charging of capacity, right?
Yeah, charging the capacity, get the time constant even there.
So what we get from here, check it out, check this out.
I think you also get it in drag force and mechanics. There's time constant even there, right?
2Rm, yeah. Is it this? Check once.
V0 by 2. Yeah, it does seem to be that.
Okay.
Yes.
Is it plus in this case? Because this is V1. V1 must be initially 0. No, -1. Okay. No, V1 was initially V0, right? Should be plus. Check once.
Squared B squared by 2. Delete that. V1 minus V0 by 2. Delete TL squared B squared by RM. Yeah, so could you move the camera a little bit?
Yeah.
But
if we have taken V1, then I should get initial as V0, right? If we have
yes, sir. Yes, so t is equal to 0 should give you
as 0. It should be in commensurate with it. We have moved with V1, right?
Yes, sir. So t is equal to 0 should give you V0, and t is equal to infinity should give you V0 by 2. Yes, sir. Yeah, it does seem to check out the limits to work.
And this will be the time constant, okay?
L square b squared by Rm.
2
2
Rm by L square b square. Not L square b square, but
yes, yeah, okay, the reciprocal of that. Yes.
okay. That'll be a time constant.
Yes.
Okay. That's it for the day then, right?
Yes, sir.
Today. And yeah.
Yes, sir.
Okay. Anything that you wish to ask?
So as I said, I didn't have time to analyze last class deeply enough. I will do it either today or tomorrow after the Sanskrit test is done. I have pretty much the entire weekend to myself, except they're starting the volunteering program again this academic year, so I'll have to go for that orientation. But except that, I have the weekend to myself, so I can study my.
EMI is okay.
Sir?
Away from the weightage, but still we'll try to assert on the import. Okay, yeah. Oh, my battery is showing 5% now. Okay, yeah. Fine. Take care.
Yes, sir. Bye, sir.
Bye. Bye.